Hi, my name's Isla, and today I'm going to be talking about my research in modeling radiated muon capture, or RMC, using Bayesian analysis techniques. So I'm part of the Mu2e experiment, which is an experiment looking for the very rare case of muon to electron or positron conversion. Now, my work is specifically dealing with mitigating and understanding background sources for these kinds of experiments. So I'm working on specifically something called radiative muon capture, which happens when a muon hits a nuclear target material. In this case, it would be aluminum-27. The muon gets paired kind of with the proton, which causes it to convert into a neutron, and that releases energy. That energy causes background. Now, it doesn't have to actually stop there. The muon can actually come right around and knock out another proton or neutron. Now, when that happens, we have more background sources, and the fact that we don't really know what the muon's going to do creates a lot of ambiguity in actually modeling and understanding this process, specifically with a parameter called Kmax, which is like the final energy endpoint. So my work is about modeling Triumph detector data for radiative muon capture using Bayesian analysis. So a little bit about Bayesian analysis. Basically, this is Bayes' theorem here. It allows you to get the probability of your hypothesis given the data that you have. And better yet, it allows you to incorporate prior information that you have about the system. Now, before we can even begin implementing this, we have to understand how our detector itself sees our data. So this is called the detector response. It's the resolution function behind the detector, and it allows us to understand detector imperfections, because naturally, no detector is perfect. So this, as you can see here, is our detector response. It's asymmetric, but it is also quite diagonal, which means it's stable. The fact that it's stable is important because it allows you to do something called data unfolding. Data unfolding is where you're actually able to unfold your data to remove detector imperfections. So for me, I use the Richardson-Lucy algorithm, which is an iterative process that allows you to unfold your data. So as you can see here, this was my original Triumph data. And using the detector response as my point smearing function, I was able to unfold my data to get a spectrum more like this. Now, this looks already a lot better and a lot clearer, and you can kind of see towards the endpoint there that there's a lot less fluctuations, which is really important because it's the endpoint value that's really important for us for RMC. So now that we have our data all clean, we can begin applying our models. So the first model that I was researching is here on the left. It's called the closure approximation. It's very simple for a model. I mean, you can just see it here. It's quite self-explanatory. C is our normalization constant, and Kmax here is just the final energy endpoint. Now, as you can see, when we actually did try to fit this using Bayesian techniques, it didn't really quite capture those last fluctuations there at the endpoints. And this is pretty much just because this model is too simple. It averages over the final nuclear energy states. Now, there's a new model called the nucleon knockout model, and this one is a lot more important as it describes our data just a lot better. It considers the case for three specific knockouts. So the first one is no knockout. We already talked about this case. That's when aluminum-27 goes to magnesium-27. Now, from there, you can have a proton or a neutron being knocked out. The most likely case is that a neutron is going to be knocked out. And so that's what I considered. So we go from magnesium-27 to magnesium-26 to magnesium-25. That would be our second and last nucleon knockout case. Now, just to make things simpler, I actually solved for Kmax here using this equation and the introduction. So from here, I was able to float the three normalization constants, C0, C1, and C2, and we got this result. As you can see, it just encapsulates the data a lot better and definitely deals with those endpoint fluctuations a lot more nicely and eloquently. Now, some further analysis on the nucleon knockout case. Clearly, we see here that the first nucleon knockout case is definitely dominant. It's a dominant source in radiative muon capture, which is good because it gives us a lot of information so that we can use that to mitigate this background later in future muon to positron conversion searches. So that's great. And so my results, very clearly showed that, using the Richardson-Lucy algorithm was by far so much more computationally efficient for unfolding. We saw that the first nucleon knockout case was by far the most dominant in muon to positron conversion. And so I'd like to thank everyone who helped me, and thank you so much for listening to my project.